I want to look at reflection and refraction of waves with you, specifically the parts that apply to GCSE Physics, the triple course. So we need to be clear about the difference between reflection and refraction and when they occur. So reflection then is that bouncing off of the wave from a surface, and it happens at the boundary between two media, two substances through which the wave is travelling. So it's not just about happening at mirrors and flat surfaces and that sort of thing. It happens with a sheet of glass, for example, when the light travels through the glass, as glass tends to allow the waves to do. When the light travels through the glass, some of it is also reflected from the boundary between the air and the glass, because the air and the glass have different densities. So what happens at the boundary between two media, if the difference in density is quite big, then the reflection, is quite significant. Other things that happen at these boundaries are absorption and transmission. So again, with the glass, you generally know that a sheet of glass is there because you can see the difference in the light coming through it compared to light not coming through the glass but just passing straight past it. So some of the light is absorbed by the glass, but most of it is transmitted through the glass. So you have transmission through the glass, unlike a mirror which just reflects it straight back at you largely. You have absorption, which happens pretty much at every surface, but we will look at how we try to reduce that absorption and reflection later. So that's reflection, happens at the boundary between two media, and as well as reflection and refraction, other things that happen are absorption and transmission. You'll need to remember those, think about those, because they're going to be part of the answer to some of the questions you have to answer. So there are two kinds of reflection. We use the word specular to describe reflection on a smooth surface. So the sort of thing we're looking at there is a mirror, for example. So here you have a very flat surface, and whether it is flat really depends on the wavelength of the wave, as you will see in a little bit when we look at the other kind of reflection. So you have this regular reflection, and if I throw in another wave here, these two incident waves on the way in are parallel, and you can see that on the way out they're also parallel. So that is specular reflection. Parallel waves coming in reflect parallel. That arrow is supposed to be going the other way, I've just realized. My apologies for that. So we have the law of reflection. And that always applies. So here we have our angle of incidence, which we call I, and here we have the angle of reflection, which we'll call R. We also call the angle of refraction R, so look out for that. So the angle I is the angle of incidence. The angle R, and these little hats, hopefully you know from maths, mean angle. Angle of reflection. And the law of reflection, which always applies for every wave under every circumstance that's being reflected, the law of reflection is that the angle of incidence equals the angle of reflection. Now, something else just to remind you of, sorry about the crazy box. This line here is called the normal. Again, this is not news to you, but normal is an old word for at right angles to. So the normal is at right angles to the boundary between the media, this being the glass, for example, and this being air, for example. So it is at right angles to the boundary, at right angles to the surface where, in this case, reflection is taking place. So this law always applies. Okay? And you need to know and be able to apply that, remembering that your angles are measured from the ray to the normal. It isn't this angle, and it isn't this angle. It is the angle between the ray and the normal. So the angle of incidence is the angle between the incoming ray and the normal, which is at right angles to the surface. The angle of reflection is the angle between the outgoing ray and the normal, which is at right angles to the surface. So that's the law of reflection. Let's now look at an example of specular reflection, but with transmission as well. So here's the picture of an oven door. You can see the glass here. You can see that light is coming through the glass. And you can see also that as the light is coming into the oven, now clearly light had to come into the oven for the oven shelves to be visible, because you only see the oven shelves because they reflect light. But also, as the light has gone in through the oven door, some has been reflected. You can see the floor reflected in the glass. But you can also see that, or you can imagine that if the oven door was open, you would see these shelves more clearly. So there is some absorption of the light as it travels through the glass and then comes back out. So you know there's a sheet of glass between you and the oven shelf. You can see that light has been transmitted, but also there's been some reflection as the light travels through the glass. As it gets to the glass, some is reflected, some is transmitted, so you can see the oven shelf because light has to get in to be reflected back out again. But some is absorbed because it's clear that there is something between you and the oven shelf here. So there you have those three effects, three of the four that we're talking about. Reflection, you can see the floor. Absorption, the shelf clearly has something between you and it. And transmission, because the light had to get in order to be reflected and come back out to show you the oven shelf in the first place. So, I've also got diffuse reflection. So, diffuse reflection is where the surface is rough. Now remember I said rough or smooth depends on the wavelength of the wave. So for light, it doesn't have to feel rough to the touch for it to be rough because the wavelength of light is so short. And what happens with diffuse reflection is if the surface is rough, and again remember this is rough in comparison to the wavelength of the wave. So this is maybe the surface of the table as far as the light's concerned. Now what I've done here is to have my three parallel rays in red, incident rays, and I've made my reflected rays a different colour just so that they're easier to tell from the incident rays. And I've got my three normals in here. So again, I emphasise the idea that the angle of incidence always equals the angle of reflection, and that's why I emphasised it, because this law applies here, but you can see that despite the fact these rays are parallel, because of the law of reflection, and because the surface is rough in comparison to the wavelength, then when these rays are reflected according to the law of reflection, they scatter. So diffuse reflection is the scattering of the light from the surface. Now this is a diagram that maybe you would need to complete to show that this is diffuse reflection. So you might be given your 3 incident rays, and then you're asked to complete the diagram. So you draw in your normal, maybe you use your protractor to measure the 90 degrees in each case. You draw in your reflected rays according to the law of reflection, and you see that the rays are not coming off parallel. And you say, well, this is diffuse reflection because the parallel rays coming in are not reflected parallel, they are being scattered. It's a key word, scattered, and so this is diffuse reflection. So let me give you a couple of examples then of diffuse reflection. So if we start with a wooden door, this, if you were to feel it, is a flat surface. It feels flat to the touch, but you can see, I'm standing taking a picture of this, but you can't see the reflection of me holding the camera. So the light is being scattered from this. We can see that the door is there, but we can't see our face in the door. The light's being scattered, so it's definitely being reflected from the wood, but we're not getting a specular reflection. We're not getting an image formed in the surface of the door, but we can see the door is there. If we look at a kind of a halfway house between the two, if we look at a polished surface, polished but not particularly clean perhaps, again this is wood of course, but because it is a polished surface, we begin to see sort of halfway between the specular and the very diffuse. We can see that there's a window over here. We can see the frame of the window, but it's not as clear as it would be if it was a highly polished surface. So this is slightly polished, slightly smoother, and so we're able to make out rough shapes in the reflection. So this is a diffuse reflection still, because it's not clear, but it's not as diffuse as the wooden door was. So you can see there's a spectrum of surfaces from the highly polished mirror kind of surface through to quite rough surfaces like perhaps the playground, where you can see the playground floor is there, or ground is there, but you can't see your face in it. So it is very much a diffuse reflection. So that's reflection. Let's look at uses of reflection. So ultrasound, which as I'm sure you know is used to look at the development of unborn babies. Sonar, used to find submarines by the Navy, used to find fish by fishermen, and seismic waves, which we use or have used in order to sort out the structure of the Earth, in order to understand the structure of the Earth. So let's look at some of these then. If we had down a little bit. The surface of the sea, perhaps. And we had the seabed. I'm just drawing this as a flat surface for convenience. It wouldn't, of course, be flat. And let's say we've got our shoal of fish, or our submarine, or whatever here. Then, and I'm going to draw this as a rectangle, because of course shoals of fish and submarines are rectangles. So, if we have a ship on the surface, and I'm not going to try to draw a ship, but imagine we have our ship on the surface, and the ship has in it a device which produces ultrasound. And the first thing that we need to say perhaps is, what do we mean by ultrasound? And ultrasound is sound with a frequency greater than 20,000 Hertz, above the maximum range, the maximum frequency that humans can hear. That is the definition of ultrasound, and you need to be able to describe that. So what happens is that the ultrasound wave is sent out by the ship, travels through the water quite happily, but when it comes to this change of density, it's reflected. Now, up here, it will time from when it emits the ultrasound beam to when it is received. And we know how fast sound travels in water, about 1500 meters per second. And so by knowing how long it took, you know how deep the submarine is. Equally, you could be testing the depth of the sea because you want to make sure you don't run your ship aground. So you can check the depth of the sea using this. And so the time it takes, the time that is measured, is the time from the ray or the beam leaving the detector to the time it returns. In that time, of course, it travels twice this distance. So if it took 1 second to go from here to there and back again, it has travelled 1500 meters in that 1 second, which means this will be 750 meters. So that's how it works. Now, it's not just about sonar, it's also about ultrasound. And again, this could be a piece of steel that I'm making in my factory. And this piece of steel perhaps needs to be really, really solid. I'm using it as a support beam for something, and it has to be perfect. So I will use my ultrasound transducer, sends out and receives, transmits and receives ultrasound. And what I will expect as I move my transducer along my piece of steel is that I will get a reflection from here, because that's going from air into the steel, and I'll get a reflection from here going from steel into air. And so if I was to be looking at the trace that I might see on my oscilloscope, I would get a reflection as it goes from the air into the steel, and then I would get a reflection as it goes in, as it goes from the steel into the air. Now I might reasonably expect a smaller reflection because there will be some absorption as it goes through the steel. Now, That's if my steel is perfect. So that's what I'm expecting to see all the time. As I move my detector down along my piece of steel, I'm expecting to see a reflection as it goes in and a reflection as it leaves again. But then if it gets to here, and I've got an air bubble or an imperfection, a crack in my piece of steel, then I'm going to get a reflection in here too. So if I'm getting reflection here, reflection here, reflection here, reflection here as I move my detector down, and suddenly I get reflection here, reflection here, reflection here, and actually what you'll get is a reflection at this boundary and a reflection here. So you'll get a reflection like that. So I know then that I have an imperfection in my steel. And I might say, well, this tells me how long it takes for it to get from here to here and back again. So I know the size of this imperfection, and by coming along I can actually plot the length of the imperfection as well as the depth of it. And I can say, well, actually that's not too big. It's going to mean the steel's still going to be able to do its job. Or I can say, no, that's definitely no good. We'll have to recast that. We'll have to make it again. So we can use ultrasound to find imperfections in solid objects like aircraft wings, like steel beams that we're making, cracks or air bubbles that you can't see but could possibly be critical to the functioning of that component. And the same thing, of course, works with looking at unborn babies, where the ultrasound is sent in, you get a reflection from the surface of the mother's abdomen, you'll get a reflection from, as it comes out of the skin again, into the fat layer, and then you would have the uterus, and you get a reflection from that, and then in the uterus, of course, you've got the amniotic fluid, and then you have my rectangular baby. And within my rectangular baby, you would have differences in density because you would have skin, you would have fat, you would have bone, you would have cartilage, you would have different densities of flesh, you'd have kidneys, and you'd have brain, and so on. So all those different densities, those boundaries between those densities will cause reflections. And so those reflections allow you to build up an image of the unborn baby. Here's an image, an ultrasound image of an unborn child. The probe would be up here. You can see the skin here. You can see the muscle and fat here. You can see the wall of the uterus, the womb here, pressed up against the mother's abdomen. You can see the amniotic fluid here around the baby. You can see the skull of the baby here, the bones. You can see the lips here. You can see the backbone, the spine. So because of the different densities, because of the boundaries between the different densities, if you know what you're looking at, then you're able to check the development of the baby here. So here we have a question. I'm going to have to move this over because you can't see all of this just now. So first question, what is ultrasound? Well, we said that it is sound with a frequency greater than 20 kilohertz. Then we have our two ultrasound frequencies that are used, 1.1 megahertz and 3 megahertz. So these are frequencies well above the 20 kilohertz that we can hear. So we're asked for the wavelength of the 3 megahertz, that's 3 million hertz, and we're given the speed is 1500 meters per second. So we know speed is 1500. We know the frequency is 3 megahertz, 3 times 10 to the 6, 3 million hertz. And we want to know the wavelength. We know that the equation, of course, V equals F times lambda, that is to say speed is frequency times wavelength. We have 1500 equals 3 million times the wavelength. So 1500 divided by 3 million is the wavelength. So that goes in there once, that goes in there 5 times, a couple of zeros off the end there. That is 5 divided by 10,000, which is 5 times 10 to the minus 4 meters. So there's another question that you might get asked, the calculation of the wavelength or the frequency or indeed the speed. So let's move on, because this is just introductory stuff that we're doing here. We're looking to know how to apply our knowledge of wavelengths. Now, I haven't mentioned coupling agents. I thought I would leave it to here. It says here that a coupling agent is used to allow most of the ultrasound waves to pass through. Now, the point of the coupling agent, if you think about, you've got your surface and you've got your probe. With the best will in the world, there's going to be some air in here, and the difference in the density between the air and the probe and the air and the skin, for example, is going to cause a lot of reflection. So a lot of the energy that you're trying to put in here to give you your image is being lost. So what you do is you use a coupling agent, a substance which covers the end of the probe and fills the gap between the probe and the surface into which you want to fire the ultrasound. And the density of this is approximately equal to the density of the flesh that you're trying to fire it into, for example. And obviously you want that to just sit there while you're working. So that's the idea behind the coupling agent, that it will have the same density as the substance you're trying to fire your ultrasound into. Why wouldn't you use water? Well, the water wouldn't sit there, would it? It will run off. If you imagine the pregnant abdomen, the water is just going to run off that. So the gel is a far better idea. And if you've ever seen this being done, you know they use gel. So that's why you don't use water. Looking then at the next part of the question, we've talked about the coupling agent and why water is no good. Now we have some testing of coupling agents going on, and we're being asked which of these things should be controlled. So let's think about what we're doing here. We are looking at different coupling agents between the transmitter and the receiver passing through the water, and we want to know which of these needs to be controlled as we test different coupling agents. Well, we have to make sure, in order that we are to make a fair test, that the width of the coupling agent remains the same. The only thing that we should change here is the thickness or the type of coupling agent. The width should not change, so that's what we're going to keep the same. I think we would also keep the depth of the water the same. So, the table shows the results for coupling agents A to G. There were two frequencies tested, 1.1 and 3 megahertz. And the results show how well the waves pass through the coupling agent compared to how they pass through water. 100% means that they were the same as water. So you can see that A went through with 1.1 megahertz. A was better than water, but it was the same as water with the 3 megahertz, and so on. So which one allowed most ultrasound to pass through at both frequencies? So we're looking for the biggest number for both of these. So 108 and 100, 105 and 100, 104 and 98. Looks like A is going to be the one. 198, 98, 98, yeah. So A is the one because it has the highest numbers for both. This number is higher than any of these, and this number is the same as that and higher than all of those. So together, A has the highest numbers for both this one and this one. So looking at this, this is higher than any of these, so it's the best for 1.1, and this is as good as B for 3 megahertz and better than all the others, so A is the best overall. And which performs the same for both frequencies. So now we're looking for the number that is the same for both, and E is the only one that has the numbers the same for both. Now we come to the main event of this. Figure 2 shows an ultrasound transmitter sending waves into a patient's body. The waves enter the body and move towards a kidney. So we have our transmitter, we have our coupling agent, we have the skin, we have body tissue, we have the kidney. The transmitter also detects the ultrasound, so it emits them and it detects the reflections. It's connected to an oscilloscope, which gives us this trace. So this, we are told, J, is the intensity of the waves emitted by the transmitter, so before they've gone into the body. And we have K, L and M. So here we have a reflection, another reflection and a third reflection. So after they enter the body, or as they're entering the body, there's before they go in, then we have 1, 2, 3 reflections. So I'd be thinking there's going to be a reflection here because of the change of density here. There's going to be a reflection here because there's a boundary, a change of density, and a reflection here. That's the way I'm thinking. And the question says, explain the intensities at K, L and M for 6 marks. So, in my early thinking, I've established reflection here, reflection here, reflection here. So there's 3 of my 6 marks. I've got to look for 3 other things to say here. So apart from the fact that I have these 3 peaks, what other detail can I take from this diagram? And the detail would be the heights of the peaks, I think. You can see that this one is much smaller than this one, and this one is smaller than this one. So how do I explain the difference in the peaks? The first thing that I would be looking at I'd be saying, well, K, if you look at K, K has a small intensity, a small peak, due to reflection at the boundary between the probe and the flesh. So I'm saying it happens at all because of the reflection at that boundary. And it's a small peak since the coupling agent reduces the difference in density. I'm going to call that delta rho, difference change in density between the two. So that's K explained. 1 mark for the fact that we're getting this reflection at a boundary between two media, and 1 mark for explaining the size of that peak because there's a small change in density. We've engineered it so that happens. L then, well, let's look at L. L is happening because the waves are reflecting from this boundary, and this is a big difference in density. So L then, we have reflection on entering the kidney. And we have a larger difference in density here. And then M is a reflection on leaving the kidney. So we have the change in density from the surrounding flesh to the kidney, and then we have going from the kidney to the surrounding flesh. So M is reflection on leaving the kidney, and M has a much smaller intensity than J or M. Remember, this is all the energy that's being put in. Some gets reflected here, some gets reflected here, some gets reflected here. So M, you're going to have absorption in the kidney, absorption of the ultrasound in the kidney is what I mean. So the peak is smaller. Okay, so that explains K, L and M. The final thing then is the speed of ultrasound is 1500 meters per second. So we have speed is 1500 meters per second. And we're asked to work out the maximum width of the kidney. We know that the time is 8 times 10 to the minus 5 seconds. And that is the time it takes for the sound wave, the ultrasound, to go from here to here and back. So that time is the time it takes to cover twice the width of the kidney. So since speed or velocity is distance divided by time, this then gives us the distance is the velocity times the time, which is 1500 times 8 times 10 to the minus 5. But actually the distance we want is half of that. So let's divide that by 2. So that's 1500 times 8 divided by 2, 4. which is 6,000 times 10 to the minus 5 for this. So 1500 times 8, which is 12,000, divided by 2 is 6,000, times 10 to the minus 5, 0.06 meters, 6 centimeters, which is about right for a kidney. So I'm happy that that answer is right. So there you have how you would do a whole GCSE question on ultrasound. What is it? Calculate the wavelength using the wave equation. What's coupling agent all about? Bit of how you do science experiments. Bit of data interpretation. And then into the actual ultrasound, really. This is the trace you would receive typically. Big peak coming out of the ultrasound transmitter, a reflection as it goes into the body, a reflection at the first boundary change of density inside the body, and a reflection at the other side as it leaves that different density piece of the body. Explaining that and then using the data you're given, the time it took between the peaks and the speed of sound to work out the thickness of this, and the key fact is that this is the time it takes to go there and back. So that's reflection then. Refraction happens at that change of density, and it's due to a change of velocity of the wave. It's very often associated with a change of direction, as we'll see in a minute or two, but it is always associated with a change of velocity. So refraction, change of density, results in a change of velocity, very often resulting in a change of direction. And an important point for you is that the wavelength is what's changing here. If the velocity is changing, then either the frequency or the wavelength is changing from v equals f lambda. It is not the frequency. The frequency is fixed by the thing making the wave, so it is the wavelength that changes. So a refraction diagram, oh hang on, my apologies. Here we have the wave coming in. This could be air, this could be glass or something. And what will happen is that as it goes from air into glass, it will bend towards the normal, like that. So the angle of incidence and the angle of refraction are different. And then, when it comes back out again, it bends away from the normal. So this angle is bigger than this angle, my first angle of refraction. And if I drew in my normal, this is my second angle of incidence, because it's incident on this boundary, and this is my second angle of refraction. This angle and this angle are the same, and this angle and this angle are the same. By geometry from your maths you can see that, but you can see it bends towards the normal here, so it slows down. That's what that tells you, which means lambda is less. And here, it speeds up, bends away from the normal, so lambda increases. So, going from air into glass, light slows down, going from glass into air, it speeds up again. Now, that's an electromagnetic wave. Mechanical waves like sound, when they go into a more dense medium, tend to speed up because they rely on the particles in your substance colliding and passing on the wave. And clearly, if they are more tightly packed, that collision can occur faster. It's not quite that simple, but you can see how an increase in density would increase the speed of transmission of the wave. Whereas with electromagnetic waves, they work entirely differently, and the density increase actually makes it harder for them to travel. So there's your diagram, which you need to be able to complete. So if you're told that this is air and this is glass, you would know when you're given this ray that it will bend towards the normal here and then bend away from the normal here. And you would choose, in the case of this rectangular block, you choose to make those two rays parallel. So that is refraction. And refraction of water waves. Here's a diagram that you need again to be able to draw and complete. So here we have, this could be waves coming into any change of density material. So here we have deep water up here, shallow water down here, and here we have my wave fronts. So these, if you like, we're looking down on top of the peaks of the wave. And this would be the line we would draw to show the direction of the wave, which is at right angles to those peaks. Here's the boundary between the deep water and the shallow water. And you can see that as the wave comes into the shallow water, it starts to slow down. So if it was traveling at the same speed, this bit would be here. But this bit is traveling more slowly than this, and so it's lagging behind. And so the effect is that the waves are bending towards the normal. My normal would be in here. And they're bending towards the normal. So in doing that, keeping them parallel, of course, as they are here, you end up with the wavelength getting shorter. And then when they come out again, well, if it was traveling at the same speed, if there was no boundary, then the bit in the shallower, the deeper water, would be here. But it's not, it's actually traveling faster in the deeper water, and so it's moving ahead of this. And so you end up with this effect. Again, in drawing them, you keep them parallel. And you end up with the wavelength getting bigger again. Now, this would be the same if we were going from air into glass for a light wave. You draw the same pattern. So here you have a diagram which you need to recognize going from deep into shallow, or if it was light, going from air into glass, back into air again. You need to be able to complete this diagram, be able to draw in these waves. So practice drawing this. What you need to do is to draw in your normal. You know you're going from deep to shallow, so you know they're going to slow down here, so you know they're going to get closer together. They're going to bend towards the normal because they slow down. So if I drew my normal in there, you would see that these waves have bent towards the normal. This bends towards the normal. And then draw these in, following on from these, but at right angles to the direction of travel again, like this. This is at right angles to these. This is at right angles to these. So there you have reflection, absorption, transmission, reflection being specular or diffuse, the law of reflection which applies in all circumstances where reflection occurs. You have uses of reflection, ultrasound, sonar. You have what refraction is. You have the idea of bending towards or away from the normal. Towards the normal is slowing down, away from the normal is speeding up. And when that occurs with light, if it goes into a more dense medium, it slows down, it bends towards the normal. With a mechanical wave, like sound, for example, it will speed up in a more dense medium typically. And so bending away from the normal. So note that difference between the mechanical and the electromagnetic and how they behave. You've got that diagram of water waves that you need to be able to complete.